We start this lecture with an overview, a plan for what will be presented. We'll first introduce the concept of vectors that will allow us to generalize what we learned last time in one dimension to 2 and 3 dimensions. In particular, we'll define vector addition and subtraction and relate the component representation of a vector to the magnitude and direction representation. We will then introduce one physics example, namely the description of free fall near the surface of the Earth as motion of constant acceleration in the vertical direction and motion at constant velocity in the horizontal direction. We will use these descriptions to calculate some properties of projectile motion. Finally, we will use the principle of superposition to relate the descriptions of projectile motion in 2 different reference frames. To this point, we have restricted ourselves to discussions of motions in 1 dimension. We have defined velocity as dx dt and acceleration as dv dt. How do we generalize these definitions to more than 1 dimension? Well, the generalization we make is most easily understood in terms of Cartesian coordinates. Here we see a Cartesian coordinate system with the mutually orthogonal directions labeled x, y, and z. To define a point P in this space, we can specify its 3 coordinates, x, y, z. These coordinates represent how far the point is from the origin in the x, y, and z directions. If we draw an arrow from the origin to the point, we can define this arrow as the displacement vector that locates the point. The coordinates x, y, z are called the components of the displacement vector in this system. With this definition of the displacement vector, it's natural to define the components of the velocity vector as dx dt, dy dt, dz dt. Similarly, the components of the acceleration vector then become dv sub x dt, dv sub y dt, dv sub z dt. With these definitions, we can see that everything we did last time for 1 dimension, x, is just repeated for the other 2 dimensions, y and z. Consequently, we can immediately write down the equations for the y and z components that are equivalent to the ones for the 1-dimensional case of x. We can formalize this generalization from 1 dimension to 3 dimensions by defining these kinematic quantities, displacement, velocity, and acceleration, as vector quantities. For example, we can write down a single equation for the velocity vector as a function of time for the special case of constant acceleration as shown. The arrow notation is apt here since it indicates that, like an arrow, a vector has both a length, also called its magnitude and usually represented using the absolute value notation as shown, and a direction. This single vector equation is equivalent to the 3 scalar equations shown. We have introduced these vectors in terms of 1 representation, their Cartesian components. In fact, you should think of these vectors as the primary object. They can have several different scalar component representations. On the next slide, we'll support this claim by introducing some important properties of vectors that we will use in this course. You know how to perform many operations on scalar quantities. For example, you know how to add, subtract, multiply, and divide numbers. You also know how to differentiate and integrate scalar functions. We can define similar operations for vectors. For example, here you see 2 vectors, A and B, represented in 2 dimensions for clarity. We can define the sum of these 2 vectors as another vector C, which is obtained from A and B using the following prescription. Place the tail of vector B at the head of vector A, and then draw the arrow from the tail of vector A to the head of vector B. Here we see how changing just the direction of vector B changes the vector sum C. Clearly, the magnitude of the vector sum C is not equal to the sum of the magnitudes of vectors A and B. You must be thinking this is a pretty strange prescription to be given the name of something simple like addition. This prescription becomes clearer if we look at the Cartesian components of the vectors. Aha! There is a method to this madness. It's clear that this definition of vector addition gives the result that the Cartesian components simply add. C sub x is equal to a sub x plus b sub x, and c sub y is equal to a sub y plus b sub y. With this definition of vector addition, we can also write a general expression of any vector A in terms of its Cartesian components and the unit vectors, I hat, j hat, k hat, in the x, y, z directions, respectively. Here we have used the fact that multiplying a vector by a scalar is the same as multiplying each of its components by the same scalar, which simply changes its length. Multiplying a vector by a negative scalar reverses its direction. The Cartesian component representation of a vector is a common representation, but it's certainly not the only one. For example, a vector can also be specified in spherical components, in which the length of the vector and the angles describing its orientation are used to specify the vector. In 2 dimensions, the orientation of a vector can be specified by the angle theta it makes with the x-axis, as shown. Using trigonometry, we can determine completely the relation between the Cartesian components, a sub x, a sub y, and the polar components, a theta. In all cases, though, you should think of the vector itself as an object, the arrow. The different coordinate systems we invent are just different ways of describing this object in terms of scalar quantities. Let's get back to doing physics by considering an example of motion in 3 dimensions with constant acceleration, that of a ball thrown across the room. Once the ball leaves our hand, the only force acting on it is gravity. Now, we'll learn more about gravity in a few lectures. For now, the only thing we need to know is that near the surface of the Earth, any object under the influence of just gravity, that is, in free fall, will experience the same downward acceleration, 9.8 meters per second squared. It is customary to refer to the magnitude of this acceleration of gravity as little g. Here we see the familiar parabolic trajectory followed by the ball once it is in the air. Before attempting to describe its motion using our new 3D kinematics equations, we need to define our coordinate system. It is customary to pick the y-axis to point vertically upward and the x-axis to point horizontally in the direction of the throw. With this choice, our kinematics equations simplify considerably. Since the acceleration is only in the minus y direction, a sub x and a sub z are 0. Therefore, the velocities in the x and z directions cannot change. The motion in these directions is just motion at constant velocity. Since we chose v0 z to be 0, we have no motion along the z direction at all. The motion of the ball will be restricted to the xy plane. We have reduced the problem to a 2-dimensional problem. Indeed, we might as well choose the initial z position, z0 to be 0, which results in the simplified equations shown. Before we use these equations in a calculation, let's first make a few observations. First, note that there are minus signs in all equations where g appears. The explanation is simply that the acceleration due to gravity is downward in the minus y direction, and we always take the value of g itself to be positive, since g represents the magnitude of the acceleration, which we know to be 9.8 meters per second squared. Second, note that the x component of the velocity is constant. It never changes from its initial value. Last but not least, note that the equations for the x and y components of the motion are totally independent. Neither one cares about the other. We will see soon that this independence has important implications. We'll now use our knowledge of the motion of an object in free fall near the surface of the Earth to make a calculation. Suppose you kick a ball off the ground at an angle theta with an initial speed v0. How far away will it land? The equations we developed in the last slide already reflect the fact that we have chosen the y-axis to be up and the x-axis to be in the direction of the kick. To make things even simpler, let's kick the ball at t equals 0 and choose the origin of our coordinate system to be at the initial position of the ball, so that x0 is equal to y0 is equal to 0. We now have equations for all 3 quantities that change as a function of time. x, y, and v sub y. We want to determine the horizontal distance the ball travels before hitting the ground. Call it d. Suppose the ball hits the ground at some t equal to t sub f. The distance d, then, is really just the x position of the ball at time t equal t sub f. Therefore, we use the x equation to tell us that d is just equal to the product of the time t sub f and v naught x, the x component of the initial velocity. Therefore, to determine d, we must first determine t sub f and v naught x. How do we do that? Well, we can certainly determine v naught x from trigonometry. Namely, all we have to do is to decompose the initial velocity vector into its Cartesian components. Since these components form the sides of a right triangle whose hypotenuse is equal to v naught, the magnitude of the initial velocity, we see that v naught x is equal to v naught times the cosine of theta, and v naught y is equal to v naught times the sine of theta. Since both v naught and theta are given in the problem statement, we now know both v naught x and v naught y. The only remaining task is to determine t sub f, the time the ball stays in the air. Since we have an equation for y as a function of t, we can just solve this equation for the times at which y is equal to 0. Since this is a quadratic equation, we will find two solutions. One says t sub f equals 0, and the other says t sub f is equal to 2 v naught y over g. These are the times at which the height of the ball was 0. One is when the ball was kicked, t sub f equals 0, and the other is when the ball landed, t sub f is equal to 2 v naught y over g. Finally, we just plug this last value for t sub f into our equation to determine that the distance the ball travels in the air is proportional to the product of the x and y components of the initial velocity and inversely proportional to the acceleration due to gravity, g. We'll explore the solution further on the next slide. When we solved the problem on the last slide, we found that the distance the ball travels was proportional to both v naught x and v naught y. It's always a good idea to check your results to see if they make sense. If we increase v naught x, the ball moves further along the x direction in a given amount of time. If we increase v naught y, the ball will be in the air longer and will travel further for any given velocity in the x direction. This all makes sense. The catch is that for a given initial speed, v naught, both v naught x and v naught y depend on the angle at which the ball is kicked. An interesting problem is to determine the angle for which this distance d is a maximum. How would we go about making this calculation? The first step is to determine a general expression for the distance d in terms of the angle theta. We can then use this expression to find the angle that maximizes d. We'll start with the expression for d that we obtained in the last slide and write both v naught x and v naught y in terms of v naught and theta. We then obtain the result that d is proportional to the product of sine theta and cosine theta. We can simplify this expression a bit further by realizing that the product of sine theta and cosine theta is proportional to the sine of 2 theta. When we do this, we obtain the usual form of the range equation. Thus we see that the distance d is proportional to the sine of 2 theta. We now plot the range d as a function of theta. We see that d reaches its maximum value when theta is equal to 45 degrees. We have already seen how the x and y equations of motion are independent. In practical terms, this means that the behavior of a projectile in the vertical direction is the same no matter how fast it is moving in the x direction, and vice versa. A bullet shot horizontally out of a gun will take the same amount of time to hit the level ground as a bullet dropped from the same height. Therefore, we can consider the motion of the kicked ball to be the superposition of two simpler motions. The first being that of a ball moving vertically with constant acceleration, and the second being that of a ball moving horizontally with constant velocity. We can actually see this superposition if we consider a single motion as viewed from two different reference frames. For example, here we see a ball being tossed vertically upward and caught again by a man. Now suppose this man is sitting in a train while the train is moving with a constant speed past an observer at a station. What will he see? Well, if the train is really moving with constant speed, then the man on the train must see exactly what he saw before. The ball goes straight up and returns to his hand. The speed of the train makes no difference as long as it's constant. What does the observer at the station see? He can't really see the same thing. He does not see the ball go simply straight up and down. He sees the train moving so that the horizontal positions of the ball when it leaves the man's hand and when it returns are separated by the distance the train travels during the flight time of the ball. In fact, what he sees is the combined motions of constant acceleration in the vertical direction and constant velocity in the horizontal direction. Wow! It looks like projectile motion can be explained as simply free fall viewed from a moving reference frame. We'll discuss this approach of relating the observations of the same motion from two different reference frames in more detail in the next pre-lecture. We conclude with a brief discussion of the main points of this pre-lecture. First, we extended our kinematic definitions to 3 dimensions by considering motions as viewed in a Cartesian coordinate system. We found we could define the kinematic quantities in terms of vectors, independent of any particular coordinate system. Second, we reviewed some properties of vectors, focusing on vector addition. Third, we examined a particular example, that of projectile motion described as motion at constant acceleration in the vertical direction and motion at constant velocity in the horizontal direction. Finally, we discovered that projectile motion could be understood as the motion of free fall viewed from a moving reference frame.